Hello everyone, my name is Petar Sekulić and today I'm going to talk about adapting large language models to specific project needs. Even though the large language models are really powerful tools, we cannot use them for any kind of task. We need to adapt them, and here I will talk about three specific use cases where we cannot use out-of-the-box LLMs. The first one is unique structure or style of the response. Sometimes we need a unique structure like JSON, or we need a response as a function call to some SDK. In this example is AWS. And we cannot get their output because LLMs are trained on the specific datasets and cannot follow the real-time data. And because of that, there are techniques to achieve this, and I will talk about it later. The second example is missing context, because probably when we ask the LLM about some question, probably when we ask the question about the real-time data, the weather, or in this example, how much was spent on machinery repairs last year, we will get some answer like, okay, I'm AI bot and I don't have access to the real-time data. And we can avoid this kind of answers with some techniques that I will talk about. And the third example is specialized vocabularies, because LLMs are trained, as Nicola said, on the huge amount of data on the whole internet, but some specific domain-specific data sets like financial or medical research papers are not in these huge data sets, and we need somehow to retrain the net and get the desired outputs. Okay, today I will talk about the three techniques, fine-tuning, the most advanced, and the one that we need a lot of machine learning knowledge and a lot of hardware to do. Prompt engineering, this is the simplest one, and we don't need any additional machine learning knowledge or hardware. And the third one, and my favorite, is retrieval augmented generation. With full fine-tuning, this technique is pretty much similar to the training of the large language model. We have the 6 steps, like dataset creation is the first step. We need to collect the data. The difference with the full training is because these datasets are much smaller and domain-specific. And we need the second step is data pre-processing. We need to split the data into training, validation, and test sets and prepare the data. We cannot put the raw text in a neural network. We need to transform the text into the tokens. The third step is model configuration, and here we need to define the hyperparameters of neural network like learning rates, number of epochs, batch size, etc. And for that we need some machine learning expertise and experience. The fourth step is model training, and here we need a lot of hardware resources, a lot of GPUs in memory, because LLMs are big neural networks with billions of parameters. And the fifth step is performance evaluation, and we will do that on the test set that we created in the second step. And if we are not satisfied with the results, we need to do this iteratively. Okay, what makes full fine-tuning valuable is data efficiency, because we will not train the neural network from scratch. We will train on much smaller data sets. We will get a better performance, accuracy, or any other metrics with this approach. And also we can get some different types of responses that we want, like we can get the JSON, we can instruct the LLM to give us the JSON format or any other format. The challenges are essentially the high computational costs and memory requirements, because we need a lot of GPUs, and even if we have the small data set of hundreds of documents, we need to spend around thousands or tens of thousands euros. Also, we need the expertise to do that. To solve some of these challenges, there is a method parameter efficient fine-tuning, and here we have a lot the family of algorithms that are developed. LoRa is the most popular one, and the process is the same. We have all 6 steps, but the biggest difference is in model training part, because we are not training the whole neural network. we are just changing the parts of neural network, smaller parts, or we are adding some small layers and just changing these parameters. That means that we don't need a lot of GPUs and memory. We just need to store a small part of neural network and change these parameters. And this is much cheaper than full fine-tuning. Okay, the next technique that I want to talk about is Bayesian prompt engineering. Here, this is the simplest one, and always we should start the project with this technique if we want to use GenAI, of course. Why? Here I want to talk about three common techniques in prompt engineering. The first one is zero-shot prompting, and this is the easiest one. Each LLM as input has the prompt and also the system prompt, the one that we are giving the instruction to LLM to help some kind of hint to get the desired output. And for example, in this, here we have the initial prompt, like the cafeteria had 23 apples. If they use 20 to make a lunch and bought 6 more, how many apples do they have? And the hint will be really basic. You're an expert in elementary school math exams, and you need to think carefully and answer interesting math questions. We can see that reasoning of, I tested this on some open source network, Mixtral 7 billion, and the reasoning is good. We have 23 minus 20 plus 6, but the final answer is wrong, and this is common problem with neural networks. The calculus, they are not so good in calculus. Okay, the next thing what we can do and avoid fine-tuning, for example, is few-shot prompting, another prompt engineering technique, where we can add also some example here to help the network and give the right answer. I tested this on the same open source LLM, and I get, again, the wrong answer. And the next technique is chain of thoughts. Besides that, to give the example, I also explain how I get the final answer. And we can see that reasoning, now the reasoning is good and the final answer is good. And this is really easy. We don't need any additional machine learning expertise to do this kind of experimentation and get desired results. And yes, this is the reason why we should always start with this technique. The next one is retrieval augmented generation, and this one is really popular, and this is developed by scientists from Meta. Here, we want to achieve this, pretty much the same goal as with fine-tuning, but the difference is because we are not changing the parameters of network, we don't need a huge machines with a lot of GPUs and memory. We have some knowledge base, and we want to store this knowledge base in some vector database. And how we can do that, let's say that we have some documents, some text, and we want to store this in a database. How we can do that? We can again run some LLM, transform the text into vectors, and store in some vector database. After that, when we get the question or query from the user, we can do the same process. We can transform the query into the vector, calculate the distance, similarity essentially, with all vectors in a knowledge base, and get the top 5 or top n documents that are most similar to the user's query, and provide as a system prompt to pre-trained LLM, base LLM. And with that, neural network can generate the right answer. Why this is popular? Because we can easily get access to the real-time data. With this approach, because in a knowledge base, we can store the data on a daily basis and get the access. And also, what are the advantages? The hallucination is the common problem with LLMs, because when we ask LLM something, the LLM can generate wrong answer and be fully confident. To avoid that, we can provide the knowledge from knowledge base, and we believe that this knowledge is ground truth. And when we provide this as a system prompt, we are confident that the response is accurate. Also, the adaptability and the interpretability is really important, because when we provide the documents from knowledge base, we can reference from which documents the LLM generate the response. This is hard with the pure LLM. Yes, and also cost effectiveness, because vector databases are much less expensive than GPUs and memory. Okay, this is some kind of summary. In this table we can see all the methods that I talked about, and here we can see some matrices like Here we can see cost and complexity of implementation. The lower values are better. And also domain-specific terminology, transparency, and interpretability, and avoid hallucination. The higher values are better because we want to have more domain-specific knowledge. We want to have the interpretability and transparency, and also we want to avoid hallucination. And yes, always we should start with prompt engineering because this is there is no additional costs, complexity of implementation. We don't need any additional machine learning knowledge. But again, we cannot solve all the tasks. For example, if we need the access to real-time data sets, it is not possible to solve with prompt engineering. The next, what we should do is use retrieval augmented generation technique. Here we can access the real-time data sets. Also, the cost is low. The complexity of implementation is slightly higher because we need to know to have the people in the team that are experts in vector databases, yes, we solve the problems of hallucination and transparency and interpretability. And yes, as a last technique that should be used is fine-tuning, and I think it can be avoided always, but yes, if we cannot instruct the LLM to give the desired response, this is the last thing that we should do, and with this approach, yes, we should know that we will spend a lot of money to do that. Thousands or tens of thousands of dollars. Thank you for your attention. Do
you have any questions for Petar?
Sure.
Can you go to the slide before? So I wanted to ask regarding this, the one before. Sorry. Regarding RAG, I wanted to ask why is it domain-specific terminology is low? Because if we have a vector database of some documents that are like in a domain, in some kind of domain, why is it?
Yes, this is a good question. Essentially, we can provide domain-specific knowledge in knowledge base, and we can avoid some kind of these issues. But the issue that I talked about is specialized vocabularies. If LLM isn't specialized for some terminology like medical research papers, we cannot get, even if we provide the ground truth values, and we need to do some fine-tuning.
Because it is using the documents from the database and then it is applying, like LLM is using them to generate the response.
Exactly,
okay.
Yes.
Yeah. Which of these approaches would kind of yield best results in the least amount of hallucinations? So which would yield the most reliable results? Is it fine-tuning in the end always the best?
I don't think so. I think retrieval augmented generation, because retrieval augmented generation depends on the knowledge base, essentially. If we have a huge knowledge base, we can avoid hallucinations. But yes, fine-tuning, again, we cannot interpret the results. We need to believe to the outcome or manually check the results.
So essentially prepare the data.
Yes.
I have one question. So, if you have a question, if you are prompting for something that is specific, like you said, medical research, then it will not hallucinate. But if you ask something else, probably it will still hallucinate.
Yes, if we fine-tune for medical research papers, we expect to get this kind of questions.
In that,
yes.
Okay.
For general kind of questions, we can use ChatGPT or any open source model that is trained on the huge amount of data.
Okay, thanks.
Anyone else?
Okay, I have one. Okay, let's mention I have a small R&D team and we decided to try to use this technology, try to use large language models to, let's say, solve one problem we think we could solve this way. And given that it's almost clear that we don't want to go with a full fine-tuning, it's too much expensive for this kind of project. Prompt engineering could not solve issues we have. What is the best, let's say, setup? Is there any straightforward way to create an environment, maybe, to take this, for example, open source model? And are there any other tools in this ecosystem that could be used, like combined, to elevate that research and to make it easier to get into this fine-tuning of models. Let's say, okay, we have already some pre-trained model, it's an open source model, we need to tune it in a certain direction. What is the easiest and most convenient way for a team that is just getting into this to start working on it?
Okay. Let's say that first of all, for this kind of things, I think the line chain is the best library to start with. And there are a lot of tools as a part of on-chain family, like agents are really good because they can scrape the internet, they can search in a database. A lot of different agents can be created out of the box with different open source or GPT models. I think GPT models are the best. But you should use them if there is no data privacy issue. But if you need to choose some open source model, you need to test. But fine-tuning, I will always suggest to avoid. Did I answer your?
Well, I agree. I totally agree, and I'm not sure if maybe I'm not getting the answer, but idea was to take the open source model. We don't have any data privacy issue. We want to tune it for some, let's say, general purpose. That's nothing too specific. We have to extend the knowledge in some direction. And I wanted to see how I could try to test it out in my office tomorrow. That
Okay,
was basically the question.
You want
huge data centers.
You want to fine-tune the open source model.
Yeah.
For the purpose, okay, again for general, some general knowledge,
Yeah.
not some specific. I think you shouldn't do that because because you have the retrieval augmented generation. If you have some data, you can transform the data into vectors, some kind of semantic meaning vector space of the documents in your database, and you can again provide this knowledge to some open source already trained LLM. You don't need to fine tune.
That was exactly the question. I didn't speak about full fine tuning. I was referring mostly to this
Retrieval augmented generation.
Yeah, exactly.
Yes, this is the method where you can provide this kind of, because the process is the same. When you communicate with the LLM, you send some prompt and get the response. In a retrieval augmented generation technique, you send the prompt, but before you get the response, this query is transformed into the vector. The most similar documents are exported from some knowledge base and provide as an input to a LLM. And LLM generate the response based on the knowledge that you have in your database.
Clear.
You don't need to fine-tune the model.
Okay, and I don't need any specific resources in terms of photo hardware, nothing like that to put up everything I need.
No, this is much more cheaper. I don't know the prices right now, but you can check. Pinnacle is one of the most popular databases, and it's really cheap to store the data here.
Okay, thank you.
Thank you, Pet. Thank you very much.